Okay, so next thing that we did was friction, and so basically we built a modified Atlas machine, and so we had a wooden block attached to a frictionless pulley, and then to the bouncy ball that got knocked off in the previous force of motion device. So when that gets knocked off, it pulls the wooden block across two surfaces, and so the first half of the first part of the surface is 0.31 meters, and it's covered in really thick carpeting, which is a lot of friction. And then the second half of the thing is zero point 0.3 meters, and it's a smooth wooden surface. And so we were comparing the position, time, and the velocity and acceleration graphs to each other of each section. And so the way that we took data for this is we measured the time that it took each section. So the carpet section, we marked a halfway point, and we lapped the time when it hit the halfway point, and then stopped the time when it hit to the end of the section. So we did for both sections 5 times each, and so that's how we got our data. And so the weight of the wooden block is 0.0279 kilograms. The weight of the constant force pulling on the wood, which is the bouncy ball and everything else that's attached to it, is 0.0426 kilograms. The length of the carpeted section is 0.31 meters, and the length of the smooth wooden section is 0.3 meters. And then the independent variable is distance traveled in meters, and the dependent variable is time in seconds. And so next we look at my friction force diagrams. And basically what I did is I took the force diagrams of all the forces acting on the wooden block. And so there's just 2 diagrams here, and the calculations are just how I came up with all the numbers. And so we were given some, and then the rest of it was just trig. So it's nothing special. And then so next we're going to look at our position versus time graph. And so as you can see in both graphs are power relationships. And then so the smooth slope, or the smooth section, is steeper. The slope is steeper, indicating more change in position per second than the carpet, which is what we would expect because the block moves faster on the smooth surface. And then the friction causes the block to slide slower on the carpeted section. And so next we look at the velocity versus time graph, and basically on top is how we calculate velocity, it's just with distance over time. And then to the right, top right, is our data table. And so we plotted the points, and the relationship between velocity and time is a linear relationship. And so the velocity in each graph is increasing since the block, as it goes in each section, is increasing in speed as it goes. And then basically the slopes, for every 1 second that passes, the block will speed up by 0.333 meters per second along the wooden surface, and would only speed up by 0.2301 meters per second on the carpet surface. And this is just because the carpet surface has more friction, so it doesn't move as fast. And so those are our equations at the bottom that we got. And as you can see, the slope and y-intercept are smaller on the carpeted section. For the acceleration versus time graph, so at the top is our acceleration calculations, which is velocity over time. And then this relationship is also linear. And then, so the acceleration is increasing for both, and it has a positive slope because it's accelerating as it gets pulled across each section. And then, so for every 1 second that passes, the block would increase acceleration by 0.333 meters per second along the wooden surface, and would only increase the acceleration by 0.201 meters per second squared on the carpet surface. Basically, it accelerates faster on the smooth surface, which is exactly what we would expect. And since that's just because of how much friction there is on the carpet section. And below the graphs are our equations that we got for the data.